Good afternoon, class. So today we're continuing along with our study of I/O systems. Here are today's topics: Kernel I/O subsystem, transferring I/O requests in software to hardware operations, the streams mechanism, and finally performance. And here's one last look at the chapter objectives. So when multiple I/O requests exist for a device, then we can schedule the I/Os, just as we do with CPU scheduling, for example. So as mentioned here, fairness is one criteria, and for example, consider Linux's completely fair I/O scheduling. Some I/O devices can't be scheduled. The best example of a schedulable I/O device is a disk drive, where the operating system might try to order the reads or writes according to cylinder number. We skipped this material in a previous chapter, primarily because some disk drive controllers themselves do some fairly aggressive scheduling, and that could perhaps undo the operating system's scheduling. Buffering is an important technique to deal with the mismatch of data being produced and or consumed by I/O devices. So this is we're considering here an instance of the producer-consumer problem. Double buffering is a technique that can be used to synchronize production and consumption. This is typically most often seen with graphics cards under animation situations, in which case the frame buffer is double buffered so that the video controller is reading data from one copy of the frame buffer and sending that to the monitor, while the graphics program is writing into the other frame buffer. Those of you who have studied computer graphics might remember what that looks like with single buffering. There's a lot of noise artifacts because of the contention for frame buffer memory. So this is what a device status table looks like. One row of this, in a sense, corresponds to the ready queue for processes waiting for the CPU. So these are devices that have been sent through the device driver, through the host controller, and onto the device controller. The operating system has to keep track of which request here goes with what data is being read or written to the device. One way that can be done would be to have a unique identifier for each request, assuming that the host controller and the device controller can maintain that identifier field. So this chart gives you a feel for the wide range of bandwidth transfer rates for various types of devices. Note that this is not a linear scale here. This is a log scale. If we graph this on a linear scale, the disparity would be much larger than we see here. So as mentioned here, caching can be combined with buffering. One would often see that at the block level of the file system. If we have a file that is undergoing heavy read and write operations, data buffered, blocks buffered to be written, can be used as caches if a read occurs to the block. So rather than writing the data out the disk and then rereading it, the write buffer will be used as a cache. Spooling is typically used in the context of printers, in which case the processes sharing a printer don't want the pages of their print jobs interleaved. An entire print job needs to print and followed by the next. That's the most typical case of spooling. I won't say anything more about device reservation. We talked about that back on the chapter with deadlock. So operating system code has ways of detecting and recovering from errors. I'm thinking of such things as the packet checksums that are used with networking communications or the smart capabilities of disk drives. As you can well imagine, I/O instructions need to be privileged in order to keep one process from reading information that it doesn't have, the correct credentials to read through the file system. Otherwise, a process could simply send I/O instructions directly to a disk drive and start reading blocks. So I/O instructions are among the privileged instructions. If a process running in user mode attempts to execute an I/O instruction, an illegal, a privileged instruction exception will occur, and the process will be terminated. So the proper way to execute I/O is through a system call. So hence for the file system, for example, we have open, read, write, close, seek, etc. System calls, and here's the user program. So one last time, the system call with a system call number is executed, right? This results in an exception, kicking the CPU into kernel mode, and then the exception handler for the system call runs, interprets the system call number, in this case a read, executes the read system call, quite possibly putting the process on a wait queue and executing a context switch, but eventually the read data becomes available and the process moves on. There's really not much new information on this slide. We've been talking about most of these concepts throughout the semester. Okay, so remember that Unix and Linux abstract devices as files. So those devices, when opened, will appear in the process's open file table with pointers to what are in essence objects for the particular, in this case, a file. So the methods available will be those that pertain to files. So select and I/O control, those will be null pointers because those operations aren't defined for files. But another entry in the file table to a networking socket will point to an object. And remember that the major number on the device file indicates the device driver to use. So these pointers are all to the device driver routines. So power management has become more and more important, whether we're Amazon or Google, or just me who's forgotten to charge his phone for several days in a row. So what's kind of cool here in my mind is Android, for example, understands how the I/O devices are connected together, and as mentioned here, has a device tree and can keep track of where the active devices are and turn off whole sections of the device as possible in order to save power. All right, so now we turn to looking how an I/O request by a user program, a syscall, ultimately result in bits flying across wires on a system bus to an I/O device. So ultimately, it all boils down to abstraction and hierarchy and layering, which we love. Here, let's consider that we're doing a read operation on a disk drive. So the user process generates or executes a read syscall. Uh, the kernel takes that over and first checks to see if the block is already buffered within the file system. If not, then the request is sent down to the I/O subsystem, then passes down to the device driver. Ultimately, the device driver, remember, will interact with the host controller, right? The control logic on the computer side, which will communicate across a bus to the disk controller. Um, what is happening with the I/O instructions is bit values are stored in bits of registers, and ultimately the bits of those registers are connected to wires, um, and uh, that results in voltage changes on the wires, communicating through, as you know, from 220 through AND gates and whatnot to execute commands. Right, and then the process is reversed when the I/O operation completes. An interrupt is generated, and that interrupt signal causes the device's interrupt handler to be invoked, and then that causes the ultimately results in the block of data being made available to the user process. So streams here reminds me of process pipelinings, as we've seen already. A difference is this notion of flow control. With a process pipeline, there's in essence an unlimited amount of buffering available within I/O processing. It's not necessarily the case, particularly if we're if streams involve hardware devices that have limited buffer sizes, so it's possible for downstream module to tell an upstream module um, to throttle its output. So here's a figure illustrating the idea. So even with all of the work that can be offloaded from CPU by using DMA controllers and interrupt-based I/O rather than polled I/O, there's still a lot of overhead involved in I/O handling. Handling interrupts, the context switches that occur, copying data from kernel space to user space. Those memory operations are expensive, and the final bullet there, network traffic, isn't necessarily a gigabit stream coming in, but small bits of data coming in and forcing context switches. So this figure shows, for example, a remote SSH connection. User types a character that generates a hardware interrupt. The CPU has to stop what it's doing, handle the interrupt, go through the device driver code into the kernel, ultimately send that character across the network, and the user shell on the other side ultimately receives that. But you can see there are a lot of layers of various calls being incurred here. So here are a number of techniques that can be used to improve performance. I'll skip this slide. And that finishes chapter 13.